Where does it say? We're recording it. Okay, good. I'll tell you in the next slide what the main topic of the class will be. Let me just say that I will need you to answer some questions in either the next slide or the one afterwards about what you know, so that we're on the same page and I know how to proceed. I'll give you a list of suggested reading, so to speak. There's really no textbook. I hope that you have seen that I have uploaded lecture notes on the class site. And we'll follow mainly those notes. I actually will show you PowerPoint slides, but taken out of those lecture notes, and I will, of course, explain and belabor on those. There is a interesting situation. Usually in the US, we give homework assignments, sort of weekly, every 10 days or so, which I think are extremely useful because they help you judge what you have understood. you can tell whether you're keeping up with the material or not. So I'll do the same. Of course, they will not be graded. I will post them on the class website usually every 10 days. So we'll wait a couple of weeks at the beginning and then give you some problems. In one of the textbooks that I will list later on, actually more than one, there will be homework problem. So please feel free to send me whatever question you have by email. I think I've listed here 2 possible email addresses. I usually prefer the Dallas address, but I'm connected to the Bologna address now as well. So I will post this homework. You're welcome to ignore them if you wish, but I recommend that you look at them, try and solve the problems. And if you wish, you can send me the solutions and we can discuss. So you can tell whether you're up to the pace required or not. I know that working remotely, I've been teaching now, I think this is the 3rd semester in which I'm teaching remotely. I noticed that there is a very limited amount of feedback. I usually like interaction between myself and the students when I teach, and the electronic medium is clearly not very well suited for that. But feel free to interrupt me, not by chat, possibly by audio, unmuting yourself, because I'm looking at the screen with full screen on the slide, so I don't see the chat. So please give me feedback, interrupt me, tell me if I'm going too slow, too fast. Again, I'm not aware of your background and interest, so I'll be happy to adjust. The material that I have is way more than I will be able to cover, so I can decide, pick and choose what we're going to do. So let me ask you a few questions, and please give me some feedback. Has everybody, or is there anyone who has never taken any class on quantum mechanics? You all have taken some class of some sort? Yes? No? Not clear?
No, Professor.
You all have taken classes on quantum mechanics. So I will not review it in deep detail. I'll try and move on. You've seen Lagrange and Hamiltonian formulation of classical mechanics. That may be a little more iffy. You've seen it. You know what Lagrange principle is. You know what Hamilton's equation of motions are, and so on. Everybody? Yes? So since there is silence, I assume that you've all seen it. You know, you've taken linear algebras. You know what an eigenvalue is. I assume that you have seen orthogonal functions. Maybe you have not gone through the whole Sturm-Liouville theory of orthogonal functions and polynomials, but I assume that you've seen polynomials that I list here, the Legendre, Laguerre, Hermite, Chebyshev, whatnot, and then functions like Bestel, hypergeometric confluent, and so on. So I assume that this is known material, although it goes low. Has anybody taken a class on quantum field theory by any chance, or many-body theory? This is, I think, not, I assume. Nobody. All right. And I assume since we are in electronic engineering, you know what a MOSFET is, and you've heard of the drift diffusion approximation, right? give me feedback, please, okay? All right, not much information. So what are we going to cover here in this class? The basic topics, you know, what matters most is a matter of personal interest. But typically, I want to get to the point where we can understand how you can calculate the band structure of a crystal. By the way, I put as a footnote that the Nobel Prize in Physics, Sir Neville Mott, considers a solid and a crystal as synonyms. Anything which is not a crystal is a liquid. It's a matter of temperature, indeed. So we'll use it as synonyms. So we're interested in electronic devices overall. Those are built out of mostly silicon and some 3,5 compound semiconductors. Now there is a huge zoo of two-dimensional materials which are being investigated. So we'll have to know what are the excited states, electronic excitation spectrum of these systems, which is the band structure. So we will review some solid-state physics to get to that point where we can understand how one can calculate that. So we'll go through the basic theory in detail, trying to explain how we can get to a single particle pseudo-potential approximation, go to density functional theory in brief, in overview, talk about empirical pseudo-potentials, and then look at some approximations, K.P, tight binding, that some of you might have heard of, and look at how you can compute this stuff on a computer. Then we'll go into something which I guess it's not something that you might have seen before because it's related to many-body theory or quantum field theory or whatever, which is talking about elementary excitations of a crystal. Mainly, of course, we'll have in mind phonons, plasmons, if you're interested in magnetic magnons, but also electrons considered as excitation of a field, which is the Schrödinger field. So this will be the bulk of the course. We'll need this stuff, both the band structure and knowing about elementary excitation in solids, because we want to deal with transport. In devices, clearly what matters is the current that flows through a device. So we want to know how charge carriers move in a device. And so we have to deal with electrons that move in a crystal, and their kinematics is given by the band structure. Their velocity, their momentum is given by the band structure that we'll have to calculate it in one. Let me actually put my laser pointer here. Let's see, where am I? Pointer options, come on. There's a pointer. So we'll need this stuff, the band structure, to know the kinematics of how electrons move. And then we'll need to deal with excitations, elementary excitations of solids, because this is what the electrons bump into. Mainly phonons. We'll talk also about other scattering processes. And then if you wish, there is the third big chunk of this class, which is how to deal with transport theory. Electrons move, how do we deal with the fact that they move? And then we will have to, I'm not sure in which order we will proceed. Logically, one should start from a quantum approach, and get into a semi-classical picture, which is the Boltzmann transport equation. But perhaps pedagogically, it's better to switch, start with the semi-classical, and having understood how to treat electron transport in a set of approximations, in a picture, if you want, in which the electrons are classical particles. Let's call semi-classical because, again, there is the band structure and they scatter quantum mechanically. So, but still, we view them as points with infinitely well-known position and momentum in violation of Heisenberg principle. But how to move from the quantum to the semi-classical picture can be done later. And then, if time will allow, we'll see how fast or slow we'll go. We'll deal on how to solve the transport equations, which are either quantum mechanically or semi-classically. In any case, they are extremely messy. They are not solvable analytically. One thing that I noticed attending some conference in mathematics is that the Boltzmann transport equation is still open up. You know, it's a integral differential nonlinear equation, and the mathematicians don't even know whether there is a solution, not to mention the uniqueness, not even to mention even more how to find that solution, if it exists. Any question about this stuff? Is it interesting? Is it something that you were expecting from the class? I noticed on the class site there was a description of what this electronic frontiers class should be. I was told, well, don't mind, it has got nothing to do with what you're going to teach. It's there, something that we put there to as a placeholder. So it's quite different from what that says. But I think you saw the syllabus, hopefully, and so you know what we're going to talk about. Good so far? Are you still there? Do you hear me? Do you see the slides? Do we still have a connection here? Yes? No?
Yes, Professor.
Yes, very good. So is that okay? Are we good with this? Okay, so the outline will be, again, I will review a little bit quantum mechanics and particularly how to do canonical quantization. That's something that is not always done. Pedagogically, one starts with Schrödinger's equation, of course, well, the hydrogen atom, whatnot, Schrödinger equation, and that's okay, you know how to quantize a single particle. If you have to quantize a general system, which is a problem that we will have to deal with, a spinning top, right? You have to quantize that thing. How do you do it? Excuse me, any question?
Yes, yes.
Okay, so how do you go about quantizing a general physical system? We will have to deal, what point is it, here in second quantization, with quantizing complicated systems, so to quantize fields. The Schrödinger field, which describes the electron, the vibrational fields of the ions in a crystal, which is going to give us phonons, the charge density waves that you have in an electron gas, which is going to give us plasmons, spin waves.
I'm sorry, Professor.
Yes, please.
There is some students who are misled in the link and they are waiting in another chat. I think that you need to clear it that for us, so if we can look for something, we can find it here or something.
No, but I have invited. So I see that there are only 13 students. I've invited people to this link. What is the problem here? I don't know how to connect to them.
Actually,
we found the link.
We were waiting at another link that was shared on the virtuale. We all were connected by that, but unfortunately I found your email there and then I am able to connect here again. So I think you have to change the link on the virtuale as well, so the other student will not going to be misguided. Thank you.
Exactly.
So I'm not sure how to proceed here. So I sent an invitation to this link. And what is the problem? The link doesn't work? So I'm confused. Professor, why it works for somebody, it doesn't work for other people.
I think it will be best if you use the link with the online classes in the timetable of the virtually, because I think there are some students who are misled by the link.
Let me see what I can do here. Yeah, I was afraid it was going to be something like that. I'm not sure how to go about it. So let me understand again. The invitation that I sent has a link that students cannot access. So how come you're here and they're not? I send the same invitation to everyone.
Okay, no, I will explain it. There were in the timetable of the course. There is the link where the online classes, when you took on it and you go, it takes you to another discussion, to another chat, which is titled by the same title of your course. We were waiting there and there is nothing.
So yeah, there was an issue because I created that link and then it disappeared. So I had issues with the IT people in Bologna, but we got nowhere. So I had to do this manual invitation because I couldn't see that link anymore. Why can't these students go back to my invitation, accept it, and follow that link?
Well, there is students who gave us the link. I think the problem is solved, but there will be a future problem when the link of this video class, where we will find it or where we can return to it.
Yeah, I was kind of nervous about this stuff because I had
I'm
lots
sorry,
of
Professor.
issues. No, I've been discussing this issue for over a month with the IT people in Bologna, and we got nowhere. I created a link some time ago, and then it disappeared, and I couldn't find it anywhere, and nobody could help in finding it. So I had to do this invitation manually. So let's see, there are right now 15 of you.
To share like every class.
So can any of you be so kind and send to the other students the link of this?
Professor, I have shared it on our group. I have shared
Pardon
this
me?
link on our group.
Please, I appreciate
Yeah,
that. I
on
appreciate
our
that.
WhatsApp group, I have shared it, and I hope they join soon.
So let's wait 5 minutes. I apologize. I'm not sure what happened.
Yeah, I have sent that this links into invitation to my WhatsApp or our WhatsApp groups. I hope they join soon.
Because, for example, there are some people who are not here, but they've accepted the invitation. So that also confuses me. They've accepted the invitation to this link, but they are not here now. Although actually one person was and then disappeared. So let me wait a little bit more. I apologize for that. Let's see if other people join us. So one of you has sent an email with a link to your colleagues.
I have shared the link on WhatsApp, Professor, on WhatsApp or group, EBIT group.
Okay. Yeah, let's use this link. For the Friday lectures, it is the same issue. I've sent an invitation. It would let me repeat it weekly only once a day, on 1 day a week. So I had to send two, one for the Thursday lectures and one for the Friday lectures. And that's the link that you should follow. The other one, I created it and then it disappears, so I don't see it now on my MS Teams calendars. Let me go there and see what's going on.
There are 29 attendees, and most of the people for Friday also, they have not accepted it, Professor.
I noticed that there were only a few people, 8 people had accepted it. So
Yes.
let me send another email to all of you. At least tomorrow will be.
I'm sorry for the disturbance. I'll go out.
Well, I am sorry. I mean, it's my fault, although I'm not sure what I did wrong. But, I decided to send this invitation for this reason. So now actually one person has left, so I'm not sure what's going on. I cannot access the other link. That's a problem. Let's see, if I go to the virtual class, what do I do? Okay, can you hear me?
Yes.
The other link. I went to the other
Yes.
link. There are two people. So I'm totally confused about what's going on here.
I think it will be better if you write to them a link in that chat, leading them to this link.
Hold on. But they had the invitation already, so that's what I don't understand.
The whole concept is new. That's why the people are misled when there is much of one link.
Yeah, well, I sent the invitation. I sent several emails, two emails, reminding people. And again, in the other meeting, I just went there. There are only two people.
Yes,
I'm
I
sure-
accepted the invitation, but since this whole concept is new to me, I went to the other
Oh boy.
chat.
Oh boy. So how many are we here now? Okay, few more. We are 19. Welcome to those who were in the other room, the wrong room. I apologize. So there are still some people, quite a few. 9 people that I had invited, and a couple of them had accepted, but they're not here. Still, again, in the other room, I finally managed to get there. Let me go there again. So I apologize if I'll get disconnected a moment, but nope. Okay, someone else joined. How many are we? Good evening, good afternoon to everyone. We're still 19, still other people are missing. It is being recorded. Somebody asked me if I'm recording. Yes, I'm recording. Well, I'm not sure what will be to be recorded except for this confusion about links. So let me do this. For now, I'll continue because we have to carry on here. I'll send another email to everyone saying, please accept my invitation and go not to the link that it is on the whatever university website, but on a link that I had included in the invitation. And we'll move from there. The lecture will be recorded, so hopefully I will be able to post a link on a class web material, whatever, and they will be able to listen to today's lecture. It will not be terribly important today because already we're wasted a lot of time and we'll not cover much material. But hopefully tomorrow morning, afternoon, things will have resolved. Is that okay? Let's proceed this way. How many people are we now? 18. So it fluctuates. Let me continue then, okay? Let me continue with the lecture and then, okay. This is the other meeting. I'm in the other meeting. Let me leave there. Let me go here. Do you see my slide?
No, Professor.
No. Let me try again. Do you see it now?
Yes.
Good. Okay. So that's where we were. I apologize. Teasing problems. Again, I will tell your colleagues if you see them, if you can interact with them by whatever, Instagram, Facebook, WhatsApp, tell them to accept this invitation that I sent with this link. I'll send another email as soon as we will be done with this lecture to everyone, reminding everyone to accept my invitation. I'll send it again and ignore the link that is given on the class webpage. Good. Where were we? Discussing what we're going to talk about, if things will work. So let me go to the pointer option again. There's a pointer. Okay. So I was discussing charge transport, and this is roughly the outline on what we're going to cover. So if you wish, it's a mix of solid state physics, electron device physics, many-body theory, all put together to reach a point where we can understand how electrons move in a crystal, in a solid, which is what we'll have to do. I will post more material. In particular, for example, there is current interest, a lot of it, perhaps even too much, on two-dimensional materials, one-dimensional structures, nanotubes, nanowires. So it will be interesting at some point to see how we can calculate the band structure, the electronic structure of such low dimensionality structures. Again, give me some feedback. If you don't want to give me feedback, oops, my clock. If you don't give me my feedback online here, send me an email telling me what your interests are, if you are missing some part of the background that I assume, or more important, if I go too slow. I'll try and start slowly. Let's review a little bit quantum mechanics, what we're going to need. And by the end of the lecture today, I would like to get at least to a review of Hamiltonian classical mechanics so that we can start with canonical quantization. Books. There is an excellent book about quantum processing semiconductors by Brian Ridley. It's an excellent text, not too difficult. Well, it depends on your perspective. This is something that I would recommend if you find it cheap or online. I don't encourage pirating copies, but I know it's a habit. That's a book that I recommend. This text that I wrote with my colleague William Vandenberg, it's already 5 years ago. This is actually, you don't really need it because the lectures that I posted on the class website already, the book has been compiled starting from these lecture notes, expanded, polished, whatever, adding also other mistakes. But so you don't really need it. An introduction to solid state physics, if you never had it or would like to refresh it, I recommend the usual Kittel's book, the undergraduate book, not the little green book of advanced solid state physics. That was probably a book taken out of lecture notes. It's an excellent book if you know already the material that he presents there. If you want to review classical mechanics, the Hamiltonian, Lagrangian, and Hamiltonian formulation, of course, Goldstein is the book on classical mechanics. There are a few issues, but it's a fantastic text. If you really dare go into second quantization and many-body theory in complete detail, of course, the Fetter and Waleka text is the Bible in this case. And for application, which are application of this theory, the theory that we will deal with, to semiconductor devices, it's Carl Hess' book. It's a little old now, but still, it's an excellent text. It's very condensed, very short, but Carl has a wonderful way of presenting things. Okay, so I'll go here fast because I understand that everyone has taken quantum mechanics before, so I don't want to spend too much time on this stuff. I'll remind you a little bit about why we need quantum mechanics. I'll briefly review a little bit this stuff, right? Hamiltonian review of classical mechanics, and go to canonical quantization. I assume that you all had perturbation theory. I will review it very briefly. It will be also one of the problems that I'll give you in homework assignments. Again, you're welcome to ignore them, but I recommend that you work on them. I'll probably post it in about 10 days or 2 weeks time. And then I'll review briefly the periodic table, how we build it. We'll go very quickly here. However, again, feel free to interrupt me if I go too fast. I know if I go too slow and you're bored, I apologize. It's better to start slowly and build up the material one piece at a time. But if I go too fast, interrupt me. Again, one of this thing that I say at the beginning of every class is there are no stupid questions. There can be stupid answers, of course. I'll try not to give too many of those, but there are no stupid questions. Don't wait until too late to tell me, Professor, 3 lectures ago I got lost at the beginning. That's too late. I cannot go back and review the whole thing. So as soon as I say something that is not clear, interrupt me. Okay, good so far? So I'll remind you that quantum mechanics came out of a crisis that happened at the end of the 1900s, end of the 1800s, early 1900s. There were 2 major issues, as you know, in the history of physics, general relativity, special relativity. There were some issues there. In particular, there were some issues with what classical electromagnetic theory, Maxwell's equation, said about the black body spectrum. In addition, there was the issue with the photoelectric effect that could not be explained. About the black body spectrum, I would like to go into some detail a little bit in deriving the classical predictions. And that's because of the math which is involved. So you know what the problem was, right? The classical theory, electromagnetic theory, Jeans law, using Maxwell's equation and conventional statistical mechanics, thermodynamics if you wish, predicted some particular shape for the spectrum of a black body, which is an ideal box in which you have electromagnetic waves, standing waves that can exchange energy with the walls, and then you have a little pinhole and you look at the radiation that comes out and look at the spectrum, and the experimental results were completely in disagreement. In particular, there was the famous ultraviolet catastrophe. Jeans law, extracted from Maxwell's equation, predicted a spectrum would have a growing, boundless growth of power in the short wavelength, high frequency domain. And the reason why that comes out is from a mathematical procedure that I would like to review briefly, because we wanted to approach the same problem dealing with other waves, electrons, in a solid, to look a little bit of quantum statistical mechanics of crystals. So I remind you that Jeans law, I don't know if you remember how it comes out simply from Maxwell's equation. You manipulate them a little bit with well-known calculus, vector calculus relationship. We're talking about in electromagnetic waves in vacuum. And what you have is that having manipulated them, you find that both the electric and the magnetic field satisfy a wave equation, the conventional wave equation. So you plug just a plain wave expression here, which is a short way of saying that I Fourier decompose in a spatial and time domain my electromagnetic waves. I look at one spatial and temporal frequency at the time, and I find that each component satisfies a particular wave equation. The idea is that once I have a wave equation, I go through the separation of variables. I hope that you remember this, right? So I have a partial differential equations. It's in 4 variables, so in 4 dimensions, 3 spatial dimensions and 1 is time. So what do? I look for a solution which is a linear superposition of functions which have a particular shape. They are the product of 4 functions, each of them function of a single variable, right? I hope this is well known. Of course, this is not the general solution, but I will build the general solution out of a linear combination of these because the wave equation is a linear differential equation. So if you plug for your electric field in this particular case, I is one of the three coordinates, x, y, z, as it says here, we can rewrite our wave equation into this particular form, which again is valid only for this particular solution. Again, the general one has to be obtained by taking a linear superposition of these, and then you find the usual thing in which you have decomposed your partial differential equations into 4 terms, and each of them is function only on one variable, and the argument is the usual one. Since these are independent variables, the only way you can achieve this relationship is if each of them is a constant. In this particular case, if what we have on the right-hand side of this equation is equal to what we have on the left-hand side. So this has to be a constant, which gives you the usual equation for a harmonic oscillator, usual things. So you have an exponential dependence in time, which gives you your oscillating wave. And you proceed the same way for the spatial components. Spatial components also have to have an oscillatory behavior. The relationship between the frequency in a time domain and the frequency in a space domain, this is sometimes called the square magnitude of the wave vector, is clearly the speed of light, this relationship over here. And this follows from the fact that we have to obey this wave equation. So again, we separate variables. We've already done it, but now we have that this equation can be verified only if each of these terms is equal to a constant, and we'll call these constants, each of them, 3 of them, such that the sum of the 3 kx squared, ky squared, and kz squared gives you the total of k squared, the total magnitude of the k vector. And this again gives you sine waves or cosines or whatever, so exponential, complex exponentials. And that's why you have plane waves. Are you okay with that? You're familiar with this? Yes? I hope it's boring. Good? Okay, I assume that it's okay. And so that's where you get plane waves. Now the idea is, we're talking about a black body here, so what has got to do with this? Well, we have electromagnetic waves which are confined into this cube. Let's assume that my box is a cube of with size of length big L, as it says here. They're in a box. One idea is I can assume that we have periodic boundary conditions so that the waves can be extended infinitely many times into infinitely many boxes in 3 dimensions. So if I assume periodic boundary conditions, I see that I have standing waves, essentially. Well, standing waves, strictly speaking, would be if I assume that I have 0 boundary, Dirichlet boundary conditions, but let's assume periodicity. So the only way I can satisfy the periodicity is if the values of the x, y, and z component of the k vectors are integer multiples of 2 pi divided by L, which is I have essentially a finite number of wavelengths inside the box in all of these 3 directions. Now, how do we get to Jean's law? I have this black body, which is this black box, this cube. There are these electromagnetic waves going back and forth in this box. There is a pinhole. I want to see what is the radiation inside. I want to peep and see what is the radiation. What do I do? Well, I have to look at how many modes, how many electromagnetic waves I have for a particular wavelength or a particular wave vector. So I define what is usually called the density of states. And that's what we're going to need for electrons as well in the future, right? So what I do is, if nu is the frequency of the mode, rho is the number of modes that I have per unit volume, per unit frequency. So rho nu d nu gives me this little number. What do? I sum all of the modes, which are labeled by this vector k, kx, ky, kz in all these directions. This delta means, strictly speaking, I have discrete number of nodes, so I look at a shell of radius k, and I look at a shell of given thickness, and I count how many of these discrete points, kx, ky, k, and z. Remember, each of them is nx times 2 pi by L, and y, 2 pi by L, and so on. How many of these I have in my shell. And the thickness of the shell eventually will go to 0 as I let the number of modes get closer and closer together as I take the limit in which my box becomes infinitely big. And this is the usual trick that I hope you've seen. So this delta, strictly speaking, should be not be the Dirac delta. I hesitate. Let's call it function. I will have something to say. It's not a function. Anyway, functional. Dirac delta. Let's call it Dirac delta without giving any other qualification to it. So the usual thing is that when I sum over a discrete number of modes over the entire region of reciprocal space, or K-space, I can convert that sum into an integral in which now the shell becomes infinitely thin, but also the number of points that I have, the number of points, where am I? Okay, sorry, the number of points that I have it goes to the continuum. So we can count modes, and this is something that we will, in general definition of the density of states, that we will have to use, as I said, also for other waves. This procedure is something that we will follow for electrons in a crystal verbatim, exactly the same way. The only difference will be what is the dispersion, the relation between omega and k. Now we have a linear dispersion. Omega is just speed of light c times k, which is the dispersion of light. In general, for electrons, we will start simply and we will deal with a parabolic dispersion, which is for parabolic bands, p squared divided 2m, free electrons. But the procedure will be exactly the same. That's why I wanted to anticipate it a little bit to make sure that you're familiar with it. So now we can either do the calculation by dealing with a delta function. We can expand this integral into spherical coordinates. The simple thing is actually to do that, look at the thickness of a shell that I have in K space, which is, of course, the surface of a shell of radius K multiplied by the thickness, the infinitesimal thickness dk. And this has to be equal to the number of modes that I have at the particular frequency. So we plug these numbers now. Again, remember that the K vector is related to the frequency. I call omega. Omega is just 2 pi nu. So this is the regular frequency. Omega is the radiant frequency. And we multiply by 2 because we have 2 possible polarization for electromagnetic waves. So we find that the density of modes grows like nu square, like the frequency square, which is exactly Jean's law, which is the ultraviolet catastrophe. So I reviewed this thing. I think you've seen it before because we will to do it again for electrons. The other issue was, if you remember, the photoelectric effect. Unless you ask me, I'll skip it. And the structure of an atom. Again, I'll skip it because I assume that you're familiar with this and you're familiar how quantum mechanics deals with this. One thing that it's interesting to do, and maybe I'll post it in the homework, but here you have the solution anyway, is this is something that has always intrigued me, how the simple de Broglie's assumption, I should say, not approximation. It was a hunch, actually, that the momentum of a particle has to be inversely proportional to its wavelength. So assuming that a particle is actually a wave at the same time, is that if you plug it into the equation that you get for the hydrogen atom, so a particle in a central force with a Coulomb potential, you get for the hydrogen atom the correct spectrum. So it's quite remarkable. Schrödinger equation, you're familiar with this. We'll have to redo it in general. So what I want to mention here is that all of you have seen quantum mechanics. All of you know what this is all about. Schrödinger essentially, I'm not sure what he did exactly when he was, I think he was in the Alps, right? It was 1924 when he went to the Alps and found the equation. Probably he guessed from Hamiltonian classical mechanics an expression for the energy. He guessed from, I think it's something that is related to Lie groups, that the energy, the Hamiltonian also is the generating function for time translations, so that you can express it as a time derivative. The momentum is the generating function for translation in space. So if you replace h with the time derivative on the one hand and p with the gradient, so the spatial derivatives on the other hand, you end up with this equation. So this is just the one way to express the energy, translation in time. This is another way to express momentum, which is translation in space. And that's how I assume he thought about it. So this is okay for an electron. So if you have a single electron, it's okay. If I give you a system of 2 electrons, things get a little more complicated, but in principle, well, you can write now the wave function as a function which is a function of 2 coordinates, R1 and R2. So you get a total of 7 variables here, the 3 coordinates of one electron, the 3 of the other, n time. And this becomes the sum of the kinetic energy of electron 1 plus the kinetic energy of electron 2. You know how to do it. If I have to quantize a rotating rigid body, things get a little tougher. And if I have to quantize the vibration of ions in a lattice around their equilibrium position, you really don't know where to start. So Schrödinger equation is okay, but has to be generalized, as I mentioned before, so that we know how to quantize the general system. And that's why we will have to deal with canonical quantization. If you wish, we can chat forever about the Copenhagen interpretation, how to interpret quantum mechanics. I remind you that the Copenhagen interpretation, besides saying several things about Hilbert spaces and bound operators or Hermitian operators over Hilbert spaces, it gives the interpretation that this wave function, that at Schrödinger's time nobody knew what it was, represents the probability. When squared, represents the probability of finding an electron in a small volume dr at position r at time t. So that it has to be normalized to 1, and then, of course, you have out of Schrödinger equation, the mathematical property of that equation, ensure that you have unitarity, or that the probability density is conserved. Again, these are relationships that I think you have seen. Again, interrupt me if you have not, or if you've forgotten them, or whatever, if you need clarification. Again. I will skip this example. I think it's clear for everyone. Unless I hear objections, I will not talk about particle in a box of free electrons. Good with this? Okay. Let me talk a little bit instead about Hamiltonian classical mechanics, because I want to lay down the foundations for what we will have to do later on, which is something that probably you have not seen, which is how to formulate a Lagrangian and Hamiltonian formulation, sorry for the pun, of fields, which is what we will need to do in order to quantize electrons, quantize the electromagnetic field, which is something that we will have to do. So we will have to deal with photons, and at least we know how to deal with interaction of light and matter. In semiconductors, it may be related. Of course, it is related to absorption and emission of photons, so anything related to light-emitting diodes and lasers. So we will have to generalize this to a system in which we have infinitely many degrees of freedom. So let me just set the notation. And also we'll have to say something about the importance, which is not often stressed, of the Poisson brackets. And I don't know if you remember what they are. So let's consider a physical system as a system which has for now, as a finite number of degrees of freedom. So a finite number of particles, as many as you wish. So we may have n particles, and big N, well, n is the number of particles, little n. So the number of degrees of freedom of these free particles will be 3 times n, 1 degree of freedom per direction per particle. We may have constraint, but I will consider only a constraint which is time independent. For example, we consider particles on the surface of a sphere, in which case, of course, there will be a additional relationship, an additional equation, which tells us that we lose 1 degree of freedom per particle. If we use spherical coordinates, the radius will be fixed. We can only have 2 angles that define the degrees of freedom associated with the degrees of freedom of that particle. So let me assume that these are already linearly independent coordinates, each for each degree of freedom of the system. So I'll call them generalized because I'm already getting rid of possible constraints that I might have on the system. Okay, so one way to do it, which is what Lagrange did it, I mean, we can use F equal ma and follow our usual Newtonian method, which is simple. But Lagrange formulated the system in a different way. Let me talk about a kinetic energy, which is the usual kinetic energy of the particles. Let's fix the ideas to particles and particles, each identified by a label alpha, as a mass. Each particle is a mass m sub alpha, and this is clearly it's the kinetic energy of each particle, and the total kinetic energy is this entire story. Now, the velocity is just the derivative of the position with respect to the coordinate, general coordinate. In general, I'm using this expression, which seems to be a little strange because these are the generalized coordinates. So, for example, the velocity will clearly be the derivative of the position with respect to time, but if I have a particle on the surface of a sphere, then first I have to take the derivative with respect to the angle, and then take the derivative of the angle with respect to time. So this is the general chain rule for derivatives, and eventually this may depend explicitly on time. So we define the Lagrangian as the sum of the kinetic energy, which usually is a homogeneous function of the square of the q dot. Sorry, here I lost this thing. Okay. Oh boy, I lost the pointer. Okay. And then I have a potential, some potential, which is a function of the coordinates. This is to be given. And the Lagrangian is the difference of the two, the kinetic energy minus the potential energy. So the idea is that my equations of motion, F equal ma, can be derived by looking at the integral of this function. It's actually a function now because it's a function of a function of time. These are 4 functions of time which determine the time evolution of the position, the generalized position, and the generalized velocity of my particle. I take the integral from one point one time to another, and I say the classical trajectory, the actual trajectory of the particle subject to this, the forces due to this potential, so the gradient of this potential, is such that this integral is an extreme point, usually a minimum, not necessarily, an extreme point of this integral. And so this is the basic idea of any variational principle. So the integral takes an extreme value, okay, for the classical trajectory. I remind you how you get now from this general abstract principle. By the way, it's very simple, similar to a similar principle you might have seen in optics, which is Fermat's principle. In general, you have to derive you have to find out what this condition implies in terms of differential equations for the q and q dots, okay? The general idea is what will lead you to what are called the Euler equation. We will call them Euler-Lagrange when applied to this particular principle, variational principle. So you want to maximize or minimize an integral of a functional, which is a function of this y of x in general. X will be our t in our particular case. I assume that you've seen it before. What you do is, well, I'm going from one particular point to another. So let me label all of the possible trajectories that I have with a label, lambda. So y of x and lambda is the trajectory, y of x. If you want to view x as t, as time, you're free to do that. Eventually, that's what we're going to do. And lambda is simply a name that I attach to each of these possible paths that go from point x1 or time t1 to time t2 with a given fixed condition that the trajectory does not change at the 2 extreme points. So I start at a given point at a given time, I end up at another point and another time. What is the trajectory that the particle will follow? Okay, so what we do is now we can simply rewrite our variational principle, the fact that this integral has to be an extreme point as a function of the path. I can write it as a maximization or minimization issue of this. This becomes now a function of lambda, because I've labeled all of this path with this label lambda. So if I take the derivative, I can do the usual chain rule. I move the derivative inside the integral. A mathematician would, of course, tell me which topology you're using. Are you sure to do that? We assume that we can do that. So we change the integral and derivative sign, and then I use the chain rule of the derivatives, so that the derivative inside will be the derivative of my function, which is the Lagrangian with respect to the trajectory, and then the derivative of the trajectory in time. And then, of course, this depends explicitly also on the time derivative of dy dx in this particular case. And so this is just the chain rule. So now I use an integration by parts by writing essentially this integration here, which, remember, this is the dy dx. There is a dot over here. I can use an integration by parts, so I can rewrite this the integral of the second term as an integral which vanishes because I'm assuming that nothing changes at the two extreme points. That's what I said at the beginning. So I'm left with this piece. If I put it together, I find that my integration involves an integrand function, which is this object. This has to be 0 for any lambda, because the variation of the path, this is a rather complicated story to say something which is simple. Everything is arbitrary here. Therefore, the only way I can have this integral vanish for any labeling that I may use, I can choose a different labeling rather than the one that I've chosen at the beginning, and yet this has to remain true, that this is 0. Therefore, the only possible way is if the integrand is 0. And that's the Lagrange, the Euler's equation. And we will call him Euler's Lagrange in the future. So this is just, remember, the derivative of f is actually our Lagrangian now. Y is our coordinate, q, or set of coordinates. d dx is d dt because x is our time. And this is the derivative of Lagrangian with respect to the generalized velocity, q dot. And so this is the Euler's Lagrange equation. Sorry, my clock will have to ring 10. So we'll let it ring. You've seen this, right, everybody? I hope it's not the first time that you see it. Anybody there? Am I still connected? Oh boy.
Yes, Professor, we can hear you.
It's a problem that I have because occasionally I lose the wireless. If I lose the wireless, we're in deep trouble. So occasionally, give me a hint. Oh, the phone. Give me a hint that you exist, so that I don't discover after 40 minutes that I've been talking to myself like a crazy person. Okay, so you've seen all this before. My pointer again. The other way, so far, everything has been considered, is dealt with by assuming that the q and the q dot are somewhat related. But we can actually do a transform, which is called the Legendre transform, and convert the Lagrangian into a function which is function only of the q, and what we call the generalized momenta, which is the functional derivative of the Lagrangian with respect to the generalized velocity, q dot. This object now does not depend on q dot anymore, depends only on q and p. If you wish, we go from a set of n second-order differential equation to a set of 2n first-order differential equation. That's what it boils down to. And then we can manipulate and see that the variation of this function, which we call big H, which we'll call the Hamiltonian, translating the Euler-Lagrange equation for the Lagrangian into the Hamiltonian, we get what are called the Hamilton equation of motion, which are written here. If I'm correct, the only case in which the Hamiltonian and the total energy of the system are not the same is when we have constraints which are time dependent. Which may be the case in an electron device when it switches, for example. So in general, we will ignore explicit time dependence of the potential and explicit time dependence of the constraints. So we'll say that the Hamiltonian is just the total energy. Now, one thing that I want to stress is the following. You might have seen Poisson brackets, and with the first time you saw them, you wonder why the heck people did that. What is the use of this? So first of all, historically, the reformulation of F equal ma in terms of Lagrangian Hamiltonian is due to a simple fact, which is extremely important, as you see it here. People were struggling at the end, mid-end of the 1800s, maybe even earlier, with celestial mechanics. The problem at the time was the motion of the moon, which is extremely complicated. And there you have a many-body system, you know, that more than two cannot be solved analytically. Nevertheless, they had to do perturbation theory without computers, by hand. So they needed to find a way to simplify the problem and find immediately if there were some constants of motion, some quantities which do not change in time. You see here, for example, that if the Lagrangian does not depend explicitly on a coordinate, doesn't depend on the azimuthal angle, for example, on a rotating body. If this is true, this is zero, which means that the derivative in time of the derivative of the Lagrangian with respect to the angular momentum, with respect to the azimuthal angle, so the angular momentum with respect to a body rotating along the z-axis, the angular momentum along the z-axis is conserved because its time derivative is zero. So the idea was, can I reformulate the problem in such a way that the symmetries of the problem are exploited immediately? I use a system of coordinates, so I choose my q and q dots, or equivalently my q and the p in Hamiltonian formulation, so that I can identify immediately the constants of motion. So one of the many differential equations that I have, if I want to study the motion of the moon, I have to account for, besides the deviation from sphericity of the moon and the Earth, but also need the presence of the sun, and in some cases, so I have already a three-body problem, or bodies which are not spherical, so it's quite of a disaster. I'm not sure if at the time they considered perturbation of Jupiter, but they matter a little bit. So they really needed to reformulate the problem from F equal ma that doesn't give you much of a hint about what the symmetry properties of the system what benefit will give you, to a system where you can see it immediately. And you see it here also. If the Hamiltonian does not depend on a particular coordinate, this q may be, again, our azimuthal angle phi. You see that the angular momentum associated with that phi, which is the z component of the angular momentum, is conserved. This is zero, therefore p dot is equal to zero. And so immediately I find some simplification of my problem. So reformulating in some more, how can I say, fancier mathematical terms, F equal ma had a reason. It was not done just for the pure cultural pleasure of expressing things in a complicated way. One thing that in particular helped them to see the symmetry of the problems is to define the Poisson brackets. I hope you know the definition, and you see immediately that the symmetry properties can be expressed by saying that when I have a Hamiltonian such that is Poisson bracket with a particular coordinate, this guy here, then that quantity is conserved. So I can express it in a different way. In particular, there is a little consideration that for a given observable, which is any function of the q and the p, remember these are sets of q1, q2, q3, p1, p1, p3, depending on how many degrees of freedom I have, any observable, which is any physical quantity, which is a function of the position and the momentum, we generalize the canonical conjugated momentum to the coordinate, satisfies an equation of motion, which is simply given by whatever explicit time dependence it might have. Usually we'll ignore it, but then it's simply given by the Poisson bracket of the observable itself, the physical quantity itself, time with the Hamiltonian. These Poisson brackets in particular have a simple form if you take the Poisson brackets of the q's and the p's themselves. The qi and pj, so the canonical coordinate and the canonically conjugated momentum to another coordinate usually have a zero Poisson bracket, not usually, have a zero Poisson bracket, unless you look at the canonically conjugated momentum to this of the same coordinate, in which case the Poisson bracket is equal to 1. It follows immediately from the definition. Instead, the Poisson brackets of any q with any other q, any p with any other p is always 0. Anticipating what I guess you know already, or you suspect, we are going to quantize the system by using exactly this formulation and converting our Poisson bracket, these curly brackets, into square brackets, the commutator between two operators of some Hilbert space, okay? Then the commutators of the canonical coordinates and its conjugate momentum, canonically conjugated momentum, it's a mouthful. The commutator between these variables will have some particular expression. You said, so what? I don't know if you ever seen the Dirac algebraic formulation of the quantum harmonic oscillator, how to quantize the pendulum Dirac's way without involving Hermite polynomials and solve the Schrödinger equation. We'll make ample use of that. I'll review it at the appropriate time. But these are the conditions which actually let you solve the problem the way Dirac did it, without solving any partial differential equations, just looking at the formal algebraic property of the system. When we'll deal with many-body theory or second quantization, this will become the canonical quantization rules, or commutation rules, or canonical anti-commutation rules. We'll consider the difference between the two, between half-integer particles, bosons, fermions, and integer particles, integer spin particles, bosons. So the bosons will satisfy the canonical commutation rules, fermions will satisfy the canonical anti-commutation rules. This will be crucial. I don't know if you ever asked yourself the question. Somebody asked me about, I don't know, some problem about an atom being hit by a photon. And I want to do it semi-classically. How do I get the field, the magnitude of the electric field, which is associated with the photon of a given frequency? How do you do that? Probably you've seen something which is sort of hand-waving. Well, I have a flux of photons. I know from the Poynting vectors from classical electromagnetism what is the energy flux. I know the photon energy from its frequency. This is already cheating. You're dealing with classical mechanics, and then all of a sudden you're putting an H bar in there by associating the energy of a photon with its frequency, which is not anything that Maxwell would have, or Faraday or anybody would have approved of or understood. But anyway, so we're already cheating there. And then you divide the energy flux by the energy of a single quantum, and then you get something for the value of the field. This is sort of okay, except that you interjected something which is totally ad hoc, which is saying, I know that the energy of a photon is that much, h bar omega, or h nu, whatever you want to call it. How do you know that? How do you know it if you want to do it rigorously without invoking this ad hoc procedure? It will be exactly the canonical commutation rules of the electromagnetic fields when quantized that will tell you what is the electric field associated to a photon. Similarly, if I have a phonon, which is a vibration, an acoustic or optical vibration of the ions in a crystal, if I have a single phonon, which is traveling in a crystal, what is the displacement in nanometers of a given ion in my crystal when a phonon comes by? Again, it will be the canonical commutation rules which tell you what is that displacement. So these are hugely important because they set the scale of everything that you'll have to deal with, all of our elementary excitations. So let's keep this in mind. I recall when I was a student and I first saw them, I said, so what? Not so what, it's extremely important. Any questions so far? Are we doing okay? I hope that I'm revisiting something that you've seen, but adding a little spin to what we will do to help you, or to help us understand where we're heading. Hilbert space, I'm not sure we'll need much of it. I will have to mention a little bit something about what is an issue with infinities that will come up whenever we deal with a system with infinitely many degrees of freedom. It's a curiosity if you wish, but historically has been a major issue. No matter what you do, as soon as you quantize fields, you start getting infinities. It's the usual renormalization issue. There is a reason for that. We'll have to introduce a particular strange Hilbert space in the future, which is Fock space, which is a space for a system with infinitely many degrees of freedom. So let's review briefly what is a Hilbert space. We can go and spend hours in abstract algebra. What is a ring? What is a field? You know what these are. What is a vector space? It's a set of vectors in which you define two operations. One is a scalar product with a vector with a scalar, which is an element of a field, of corpus, and you define a vector addition. And the system is linear, the usual properties that you have for a vector field. You call dimension of a vector field the maximum number of linearly independent vectors that you can have, and they form a basis of vectors. You can orthogonalize them by assuming they're orthogonal, introducing an inner product, which is the dot product. And then in order to do calculus, to take limits, to do derivatives, to do integrals, we need a topology. We have to know that the system is dense, so that any sequence, any Cauchy sequence has a limit in that set. And the way we introduce the topology in the spaces that we're interested in, Hilbert spaces, is by defining an inner product, which is the dot product. It's the dot product between two vectors in usual three-dimensional vectors. It will be the integral between two functions in a functional space. We define this as a vector, as a product, as an inner product or dot product. The dot product of a vector by itself defines a length or a norm. If you take the norm of a difference of two elements, you get sort of a distance between the 2 points. Once you have a distance, so you have a metric, then you can see if your system is compact. So if you really have a complete topological space in which every Cauchy sequence has a limit, and then you can do calculus. So Hilbert spaces are extremely rich from a mathematical point of view, which is what we need because we want to do calculus. We want to do spectral theory on that, okay? So that's why we need such a richness. One issue that I find always ironic is that after having defined a Hilbert space in quantum mechanics and having told you the typical Hilbert space of particles, of a single particle is L2 over 3, the Hilbert space of all square integral functions in three-dimensional space. The first thing that you show is a delta function and a plane wave, which are not elements of that space. It's a complicated story. I know you have to go to the duals and their equipped or rigged Hilbert spaces, but let's not go there. The important things, as you know, is that the physical quantities, things that we can observe, so the observables, besides energy, momentum, angular momentum, but spin, whatever, they are bound, Hermitian, linear operators on a Hilbert space, okay? And we need the operators to be bound because their eigenvalues form a complete set. We need them to be Hermitian because their eigenvalues are real and their eigenvectors are orthogonal if they correspond to the different eigenvalues. I've written this here, so the richness of the system is guaranteed and the physical correctness of our, this is the Copenhagen interpretation if you wish, is correct. Because if we associate physical quantities to Hermitian operators on a Hilbert space, we're guaranteed to have real numbers as a result of our experiment. Although we can use complex numbers in some particular cases, but in this case, we really want them to be real. And the system, the set of the eigenvectors of a bound Hermitian operator is a complete set and it's orthogonal, so I can also normalize it, and it becomes a good basis of functions in my Hilbert space. We will have to generalize this a little bit dealing with Fock space. So what is canonical quantization? Again, we need to do this because, as I keep repeating, I think it will be the third time that I say it, you know how to deal with one electron. You may know how to deal with two electrons, and you may know how to deal with two electrons with spin, maybe. But if I have to deal with the ionic vibrations in a crystal, where do I start? So this is not what we do here, because we will idealize our crystals with an infinitely large system, so with infinitely many degrees of freedom. So we'll have to do the Lagrangian and Hamiltonian formalism for fields. But this is the general idea. I reformulate my entire mathematical definition of my physical system in a Hamiltonian way, Lagrangian and Hamiltonian. Once I have that, I promote the coordinates and the canonically conjugated momenta to operators over a Hilbert space, which is associated with my system. In the case of systems with a finite number of degrees of freedom, there is only one Hilbert space up to isomorphisms. So they're always all the same. The Schrödinger, the Heisenberg, the interaction pictures, they're all the same. Unfortunately, for a system with infinitely many degrees of freedom, that's not the case, and that's the source of the infinities that we will have to deal with. So, but in any case, you take this Hamiltonian formulation, all the variables, the physical variables, become operators, Hermitian operators over Hilbert space that you define from the beginning. For a single particle, it will be L2/3, and you can cross it, do the tensor product with SU2, which is the space of spin states, just two column vectors with which is the space where the Pauli matrices live. But in any case, you know what the Hilbert space is, and you enforce the canonical commutation rules. Again, it's not particularly useful if you deal with differential equations. I hope you remember that, as I mentioned before, that if you quantize the harmonic oscillator a la Dirac, you need this to build the entire case and see what the eigenvalues are and how to express the ladder operators. The operator will bring you up by one eigenvalue and down. We'll generalize them to creation annihilation operators, but these are what you need. So don't underestimate the importance of these canonical Poisson brackets as they are in a classical system that become canonical commutators. So the canonical commutation rules for a system, for a quantum system. The only thing we've done is add IH bar to our derivatives. The time derivative also has an IH bar, which is the Hamiltonian. The momentum has IH bar times the gradient, whatever is the derivative with respect to the coordinate. And the canonical commutation rules also acquire an IH bar. Okay, and then you see that in the Heisenberg representative. Well, I told you that the Heisenberg and Schrödinger and also the interaction picture are all the same. You can look at a Heisenberg interaction, Heisenberg picture, Heisenberg representation. It's a representation in which the states of the system, which are vectors of your Hilbert space, are fixed in time. You specify that t equals 0 and the state stays fixed. Instead, the dynamics is given by the time evolution of the observables, of the operators. And they are exactly the equation of motion that we saw for classical mechanics for the observables, except that we have replaced the Poisson bracket with minus IH bar, or 1 over IH bar. Okay, in the Schrödinger picture, instead, you do the opposite. A state U, the original initial state of the system, now has an initial value, but you freeze in time the observables, they don't move in time, the Hamiltonian, the angular momentum, whatnot, they remain fixed, but it's the states that evolve in time now according to Schrödinger picture, Schrödinger equation, which is this is written in a general form, where H is the Hamiltonian, which can be whatever. Notice that I'm still being pedantic and putting little hats the hat means it's an operator, okay? And they become bold. So bold doesn't mean vector necessarily, it means operator. I will not be so strict and with the notation in the future. Again, you can immediately convince yourself that the Heisenberg-Schrödinger representations are the same. Again, this is not true if you move to a system with infinitely many degrees of freedom. Alas, that's the whole thing of constructive quantum field theory. You can write essentially the expectation value. You can put it many ways. The expectation value of an observable A for a system in a state U. How does it change in time? You can plug it in, the time derivative. This gives you in the Heisenberg representation. This is the operator which moves in time. It satisfies the DDT, assuming that it doesn't depend explicitly on time. It's just the commutators of the Hamiltonian. You write up explicitly, expand the commutators, and that's what you get. Now we can change perspective, and any of these expectation values can be reinterpreted as by saying, well, it's not really A that changes in time, it is actually U that changes in time. And you get exactly the same thing. So the two representations are the same. You get the only things that you can measure are expectation values of operators. And they change in time exactly in the same way. And so the dynamics is preserved. Okay, how much time do we have here? Okay, we have 5 minutes left, a little bit more. Again, a question for you. You have seen all perturbation theory, right? Yes? Anyone? Yes? Do I exist? Am I still online? Boy. Yes?
Yes.
Yeah, good, good. Again, it's my fear that I disappear into hyperspace and talk to myself. So you have seen perturbation theory, all of you. Should I review it? Are you okay with me skipping it altogether? Yes? No? I'll skip it. Let me just mention one thing which is quite important. Let me just review the results. So perturbation theory, as you remember, is I have a system that I don't know how to deal with Hamiltonian, which is H. But I know how to solve a system which has a Hamiltonian which is close enough. Some Hamiltonian H0, and the real Hamiltonian of the system I want to solve is H0 plus another Hamiltonian multiplied by a constant, which we call a coupling constant or a perturbation parameter, which is small enough. So I know how to solve a system which is close enough to the one that I really need. Two possible scenarios. One is this perturbation Hamiltonian depends on time, and one in which it does not depend on time. The one in which it does not depend on time is called stationary or time-independent perturbation theory, and the basic result is that for a given state which has a energy E sub m, which is an eigenstate of the Hamiltonian that I know how to deal with, H0, well, this is changed by terms, and I can write a series of increasing powers of alpha, which is my perturbation parameter. And the first correction is just the matrix element of this perturbing Hamiltonian with respect to the states, to the state M. So it's just the diagonal term HMM. If I want to go higher up in second order perturbation theory, then I have an expression like this in which I sum, if you want, the matrix element over intermediate states n, and so I sum over on n different from m, and I have this expression. This is the same thing that happens to first order if I want to write the correction, first order correction to the wave function. So this is the wave function that I know what it is because it's an eigenstate, or it's an eigenvector of H0. Phi sub m is what I'm looking for, which is the eigenstate of the full Hamiltonian H0 plus alpha H. I don't know what it is. If I expand it in perturbation theory, I find that it's a linear superposition of the unperturbed states with a coefficient, which is this. So this is something that we will use to explain, for example, why bands repel. You see, for example, that the correction, particularly this expression, states which have an energy which is higher than the state I'm considering push its energy down, and states with which energy is lower than the state that I'm considering, this is positive, so they push it up. So if I'm looking at the energy of one particular state, all of those which are below tend to push it up, and all of those which are above tend to push it down. Clearly, the state which is closest to the energy of interest is the one that wins. This will be used, for example, to calculate the dielectric constant of the dielectric of silicon dioxide. And here we'll plug the gap, because it will be the eigenfunctions of the valence and conduction bands that matter most, because they make the denominator smaller. So this is something that we will use. We will use it for calculating the dielectric response of a solid, which is quite important because it's what screens interaction. So we will use time-independent perturbation theory to calculate that with some corrections that, because we will deal also with time-dependent phenomena. For the time-dependent, so the derivation is, I've written here, just look at the notes if you wish, and you have them. Time-independent perturbation, time-dependent perturbation theory instead, something that you can summarize. At the end, you end up with Fermi-Golden rule, which is, I hope it's well known to everybody. If I have a system which at time equals 0 is in a state J, and I have a Hamiltonian, which I'm assuming is a sinusoidal dependence on time, or e to the I omega t, then the transition at the probability per unit time that my state will make my system will make a transition from state J to any other state K is just given by the square of the matrix element between the two states, the initial and the final. Energy has to be conserved. If the perturbing Hamiltonian has a dependence e to the I omega t, it means that it carries an energy h bar omega, plus or minus, depending on which way it goes. So this expresses energy conservation. And then there is this ubiquitous factor of 2 pi over h bar. I hope you're familiar with this. I'm not going to spend too much time worrying about the Dirac temper distribution, which is an element of the dual of a Hilbert space, blah, blah, blah. We'll call it Dirac function. I had a professor when I was a student that essentially failed during class. If you ever dare say the Dirac delta function, it's not a function. It's not a function, but it's a functional. But we'll be sloppy, and I'll call it Dirac delta function more than once, and I hope you don't mind. Okay, I guess I'll stop here. Next time we'll review tomorrow, and I hope that everybody will be here and will review the entire situation. I'll go quickly through the hydrogen atom, the periodic table, and we'll start next week, on following Thursday. Let's see, do I have enough material here to cover? I don't know. We'll see how we go. Talk about the real core of the class. The idea here, I will post the slides of up to today, but again, they are simply the lecture notes. Occasionally, though, I will insert different slides, I will use different stuff, and I may sketch a few things if required. And finally, please give me some feedback, okay? I always fear that I disappear, my Wi-Fi goes down, my connection goes down. So occasionally give me a sign of being alive and well, and ask questions. Don't be afraid. As I said, no stupid questions, just stupid answers. I'll do my best not to give those. Okay, so I'll see you tomorrow. I'll stop the recording. I'll see